In this video, I'm going to explain what differential elements and integrals are and how to use them in different coordinate systems. Differential elements are small segments of a bigger object, such as a line, a surface, or a volume. They are useful for calculating things like length, area, volume, work, flux, etc. by adding infinitely many small pieces. There are different ways to describe the position and orientation of an object in space, such as Cartesian coordinates, cylindrical coordinates, and spherical coordinates. Each coordinate system has its own advantages and disadvantages, depending on the shape and symmetry of the object. I already covered cylindrical and spherical coordinates in the previous two videos. In Cartesian coordinates, we use x, y, and z to describe the position of a point in space. The unit vectors along the x, y, and z axes are denoted by ax, ay, and az, and they are constant and do not depend on the position of the vector. The differential element of line in Cartesian coordinates is dl equal dx ax plus dy ay plus dz az. This means that if we move a small distance, dx along the x-axis, dy along the y-axis, and dz along the z-axis, the length of the segment is given by dl. The differential element of surface in Cartesian coordinates depend on which plane the surface is parallel to. If the surface is parallel to the xy plane, then ds equal dx dy az. This means that if we move a small distance dx along the x-axis and dy along the y-axis, the area of the patch is given by dx dy times the unit vector perpendicular to the plane, which is az. Similarly, if the surface is parallel to the xz plane, then ds equal dx dz ay, and if the surface is parallel to the yz plane, then ds equal dz dy ax. The differential element of volume in Cartesian coordinates is dv equal dx dy dz. This means that if we move a small distance dx along the x-axis, dy along the y-axis, and dz along the z-axis, the volume of the cube is given by dx dy dz. In cylindrical coordinates, we use rho, phi, and z to describe the position of a point in space. Rho is the distance from the z-axis. Phi is the angle from the x-axis in the xy plane, and z is the height from the xy plane. The unit vectors along the radial, angular, and axial direction are denoted by a rho, a phi, and a z, respectively. A rho and a phi are not constant in the Cartesian coordinates, but in the cylindrical coordinates, a rho is always perpendicular to the cylinder, and a phi is always tangential to the cylinder. The differential element of line in cylindrical coordinates is dl equal d rho a rho plus rho d phi a phi plus dz az. This means that if we move a small distance d rho along the radial direction, rho d phi along the angular direction, and dz along the z-axis, the length of the segment is given by dl. The differential element of surface in cylindrical coordinates depend on which plane or cylinder the surface is parallel to. If the surface is parallel to the rho phi plane, then ds equal rho d phi az. This means that if we move a small distance d rho along the radial direction and rho d phi along the angular direction. The area of the patch is given by rho d phi times a unit vector perpendicular to the plane, which is a z. Similarly, if the surface is parallel to the rho z plane, then ds equal dz d rho a phi, and if the surface is parallel to the phi z plane, then ds equal rho d phi dz a rho. The differential element of volume in cylindrical coordinate is dv equal rho d phi dz. This means that if we move a small distance d rho along the radial direction, rho d phi along the angular direction, and dz along the z-axis, the volume of the cylinder is given by rho d phi dz. In spherical coordinates, we use r, theta, and phi to describe the position of a point in space. R is the distance from the origin to the point, theta is the angle from the z-axis, and phi is the angle from the x-axis. The unit vectors along the radial, polar, and azimuthal directions are denoted by AR, A theta, and A phi, respectively. AR is perpendicular to the sphere surface, and A theta and A phi are tangential to the sphere surface. The differential element of line in spherical coordinates is dl equal dr AR plus r d theta A theta plus r sin theta d phi A phi. This means that if we move a small distance dr along the radial direction, r d theta along the polar direction, and r sin theta d phi along the azimuthal direction, the length of the segment is given by dl. The differential element of surface in spherical coordinates depend on which plane the surface is parallel to. If the surface is parallel to the theta phi plane, then ds equal r squared sine theta d phi a r. This means that if we move a small distance, r d theta along the polar direction and r sine theta d phi along the azimuthal direction, the area of the patch is given by r squared sine theta d phi times the unit vector perpendicular to the plane, which is AR. Similarly, if the surface is parallel to the r phi plane, then ds equal r sine theta dr d phi a theta, and if the surface is parallel to the r theta plane, then ds equal r dr d theta a phi. The differential element of volume in a spherical coordinate is dphi equal r squared sine theta dr d theta d phi. This means that if we move a small distance dr along the radial direction, r d theta along the polar direction, and r sine theta d phi along the azimuthal direction, the volume of the sphere is given by r squared sine theta dr d theta d phi. If we have a vector field A in space, we can also define line and surface integrals for it. These integrals measure how much the vector field flows along a curve or through a surface. Also, if we have a scalar field B, we can define the volume integral for it, which measure the total value of the scalar field over a given volume. The line integral of a vector field A along a path L is denoted by the line integral of A dot dl. This means that we multiply the vector field by the differential element of line and take the dot product then add up all these products along the path. The line integral gives us the work done by a vector field on particle moving along that path. If the path of the line integral is closed, we call the line integral the circulation of A along L. Circulation is a measure of how much a vector field swirls around a closed line. The surface integral of a vector field A over a surface S is denoted by the surface integral of A dot ds. This means that we multiply the vector field by the differential element of surface and take the dot product, then add up all these products over the surface. The surface integral gives us the flux of the vector field through the surface. If the surface of the surface integral is a closed surface, then the integral becomes the closed surface integral of A over a closed surface S, which measure the flux out of the enclosed volume by a closed surface. The volume integral of a scalar field B over a volume V is denoted by the volume integral of V dV. This means that we multiply the scalar field by the differential element of volume, then add up all these products over the volume. Let's look at an example. We are given a vector field A in cylindrical coordinate, which is rho cosine phi times the unit vector A rho plus z sine phi times the unit vector Az. We are also given a curve C that consists of 3 line segments. C1 from the origin to the point with coordinates 2, 0, 0. C2 from that point to the point with coordinates 2, 60 degrees, 0. And C3 from that point to the point with coordinates 0, 60 degrees, 0. And we are asked to find the circulation of A around C. To do this, we need to find the line integral of A along each segment and then add them up. We also need to choose an orientation for C, which is counterclockwise by convention. For C1, we can see that the curve is along the rho axis with phi and z equal to 0. The differential vector along C1 is a small change in rho times the unit vector A rho. The dot product of A and the differential vector is going to leave the rho component only, so the line integral along C1 is the integral from 0 to 2 of rho cosine phi d rho, which is equal to half of the square of rho evaluated from 0 to 2, which is equal to 2. The differential vector along C2 is a small change in phi times rho times the unit vector A phi. The dot product of A and the differential vector is 0 because the vector field does not have phi component. So the line integral along C2 is equal to 0. For C3, we can see that the curve is along the rho axis with phi equal to pi over 3 and z equal to 0. The differential vector along C3 is a small change in rho times the unit vector A rho. The dot product of A and the differential vector is going to leave the rho component, so the line integral along C3 is the line integral from 2 to 0 of rho cosine pi over 3 d rho, which is equal to quarter times rho squared evaluated from 2 to 0, which is equal to negative 1. Therefore, the circulation of A around C is the sum of the line integrals along C1, C2, and C3, which is equal to 2 minus 1, which is equal to 1. This means that the vector field swirls counterclockwise around C with a strength of 1.